Hello and welcome to this Institutional Mechanical Engineers technical lecture titled Overview of Steam Fundamentals. Here we will explore properties of steam, how it is produced, distributed and managed in process applications. This lecture is part of a series of 7 CPD sessions which are approved by Chartered Institution of Building Services Engineers and Engineers Ireland. The webinar is being recorded and it will be made available later through the IMechE's YouTube channel. Please use the link provided in the chat to submit your feedback at the end of the event, which will also allow you to request the presentation slides. I will put the link in the chat just in a bit shortly. Thank you. I am Murat Islam. I'm a member of the IMechE Lancashire area and I will be managing this 1-hour event. We will have a 10-15 minute Q&A session at the end, so please use this chat to submit all your questions and I will direct them to our speaker later. Our speaker, Mr. Daniel Wells, is the National Consultant Specialist for Spirax Sarco, providing educational, technical and commercial support for consultant design engineers, engineering, procurement, construction and contractors across the UK and Republic of Ireland. Working closely with the Spirax Sarco's area engineering and projects teams, Dan has many years experience with a broad range of industrial applications, working across many engineering disciplines. Ladies and gentlemen, our speaker for this lecture, Dan Wells. Thank you very much. You can take it, Dan.
Great. Thank you very much for that introduction, Murat, and thank you also for the opportunity to present to your members this evening. Much appreciated.
Thank you.
Before we make a start with this evening's presentation, I'd just like to make a very quick introduction to Spirax Sarco to give you an understanding for who we are as an organisation. Well, we're a UK-based organisation with FTSE 100 listed. We've got representation and offices in a number of different countries around the globe. So we've always got an engineer or a service personnel on hand to support wherever our end using clients may be, contractors or any other engineers that may require support from us. As far as the UK and Ireland team is concerned, we're a team that's approximately 200 strong. About 50% of the team work from home, away from our head offices in Cheltenham. So again, we're always on hand to support wherever our end user clients or their offices or their applications may be based. But we've also got a number of different resources that are available to support engineers. For example, we've got an interactive YouTube channel whereby you can dial in and get a better understanding for certain solutions visually. For example, how the internal mechanism of a steam boiler operates. We've also got a number of calculators and configurators that are available online. We've also got a number of very useful calculators and configurators that are available in the form of an app that can be downloaded free of charge to your iPhone, your Android phone. And those calculators and configurators are very, very useful on a number of different levels. First of all, they can help you to understand the basic design requirements of a steam distribution network. For example, sizing the steam pipes, sizing the condensate pipes, sizing the control valves and the steam traps. But they can also help you on a financial level. They can help you to understand the cost of a unit of steam, the cost of a unit of condensate, and thereby we're able to calculate any payback that can be enjoyed by replacing a failed steam trap, for example, or increasing the mass of condensate that can be successfully recovered back to the boiler house. So I would encourage you to download that little app that you can see up in the top left-hand side of the screen, top right-hand side of the screen. And the one thing I would say is please make sure that you download the Spirax Sarco Mexico version, not the Spirax Sarco UK and ROI, for the simple reason that there's more functionality on the Mexican version and you can change the units and languages back to whatever you prefer. So this slide is really intended to remind us that steam is a very, very useful and diverse source of energy, and it's used for a number of different reasons and across a number of different industrial applications and across a number of different sectors, ranging from, for example, the production of domestic hot water in a university to sterilizers in a hospital or humidification in a pharmaceutical plant. We can even use it for direct injection purposes, injecting steam directly into a bread oven in a bakery. And all of these different applications mean that steam can face a number of different challenges. But the message is clear. Steam is used in a far, far greater range of processes than many of us actually give thought to. So as Murat mentioned, this evening's presentation, it's the first in a series of 7 different CIBSE approved CPD presentations that we offer on the wider steam and condensate loop. But this evening, we're going to go back to basics. We're going to start at the very, very beginning to understand the fundamentals of steam, the properties of steam. And we're going to understand the importance of ensuring that we generate steam so that it leaves the boiler house in the best possible condition. So some of the terminology we use, you may have noticed that I mentioned the steam and condensate loop. And that's because we generate steam in a boiler house, in an energy centre, and that could be located hundreds, if not thousands of meters away from the various processes or plant rooms that are going to use that heat energy. So if you think about an oil refinery or a large hospital, we can be distributing the steam some considerable distance. And that's one of the reasons why we want to ensure that we're generating the best possible condition of steam that we can. It's only by doing so that the steam is going to arrive at the point of use at the best possible condition. But it's important to understand that steam is a gas. And the steam leaves the energy centre, leaves the boiler house. It's distributed some considerable distance under pressure. But it's important to understand that when steam gives up its heat energy, it does so by condensing. So it changes state from gas to that liquid condensate. And that liquid condensate, it's a byproduct of heat exchange. It doesn't have any value for the vast majority of heat transfer applications. We need to get it away. But whilst that liquid condensate doesn't have any value at the point of heat exchange, that byproduct is still hot water. So it does have a value if we can recover it from the process, all of those hundreds or thousands of meters back to the boiler house, hence the terminology loop. We've got steam as a gas going out to the process. We've got condensate as a liquid coming back. So at this point, I'd like to go through some of the basic properties of steam to help us really understand what sets steam aside from any other sources of heat energy, such as low temperature hot water or thermal oil, for example. And that's basically because, as we've already mentioned, steam's a gas, and that gas is compressible. So if we're generating steam at a higher pressure, we've compressed that volume down. So a higher pressure steam, it occupies a small volume and therefore can be distributed in a very small diameter pipework, whereas a lower pressure steam is going to exist at a larger volume and is therefore going to be distributed in a larger and therefore more costly, more intrusive infrastructure. Another benefit, well, we know that there's a direct pressure to temperature relationship with steam. If we know the pressure that the steam is being generated at, distributed at, or condensed at in the process, then we know the temperature that that steam has. If we want to control the temperature of the steam at the heat exchanger, we can achieve that simply by manipulating the pressure. We also know that there's a significant amount of heat energy present in a unit of steam, a kilogram of steam, for example. And that's because we generate steam at far, far higher pressures and temperatures than we do with alternative sources of energy, such as low temperature hot water. So if you think about a water to water heat exchanger, could be designed to give up just 11 degrees of temperature to the process. Well, if we compare that to a steam to water heat exchanger, there's as much as 50 times more useful heat energy in that kilogram of steam than there is in a kilogram of water. So if we think about that for a moment, that means that we only need to generate far, far less steam to get the same heating effect than we would do with a water-based heat exchanger. And because steam is compressible, we can also distribute that steam in a very, very small infrastructure. And that information has really got its basis in the understanding that water, which is the raw ingredient of a steam system, water's got a specific heat capacity of 4.19. And that means if we want to increase a kilogram of water by just 1 degree, we need to put 4.19 kilojoules of energy into it. So again, because we generate steam at higher pressures and higher temperatures, that explains why there's so much heat energy in steam compared to water. And we're going to come on and touch about this on the next slide. We also know that another condition of steam being a gas, well, we know we don't pump gas. Steam moves in accordance with the pressure drop. So if we're distributing steam at a high pressure in the boiler house, that pressure is partly responsible for pushing the steam all around those hundreds or thousands of meters of pipe towards the process. We don't need circulating pumps. And of course, we know that we need to pump a liquid such as water. So not only would we have to purchase, install, test and maintain a circulating pump on a liquid system, we'd also have to pay for that electrical energy to move the heat from the point of generation to the point of use. Something we don't need to think about with the steam system. The steam will move entirely on its own accord, providing we've sized those steam pipes correctly. We also know that steam as a gas, well, it's going to spread out and occupy all of the heat transfer surface area that's available. So that means that we get a very even and uniform release of heat energy across the membrane into the process. It means that that's one of the reasons why we don't get as much striation or as many cold spots with a steam system as we do with a water-to-water heat exchanger. And we also know because steam gives up its heat energy by condensing, the speed of heat transfer across the heat transfer surface area is approximately 3 times greater than it is with a water-to-water heat exchanger. So those 3 reasons help us to understand why it's possible and attractive to have a steam-to-water heat exchanger that's very, very small in footprint. We've got significantly more heat energy in a kilogram of steam than water. We've got a very, very efficient use of the heat transfer surface area, and we've got a very, very high speed of heat transfer. So traditionally, water systems have taken on the heat energy into the process by having to hold that hot water on the secondary side in storage. And that's something we don't need to do with the steam-based system. We're now able to generate hot water from steam instantaneously on demand. But the one thing that I want to leave you with on this slide is the understanding that when steam gives up its heat energy, it does so by condensing, but it doesn't give up all of its heat energy. It only actually gives up what we refer to as its latent heat. So that takes me on to the steam tables, and this is typically the single most important slide that I ever show in my presentations. And that's because there's so much valuable information shown here. So if we look at the steam tables that's demonstrated up towards the top left-hand side of the screen, this shows us a lot of powerful information. And we're going to start off with the first column as we move from the left towards the right. That shows us the pressure. Now, this could be the pressure that the steam's generated at in the boiler, the pressure that the steam is distributed at in the pipework, or it could be the pressure that we're condensing the steam at in the heat exchanger. Let's use the example of 0 bar gauge, atmospheric conditions. So if we take a kilogram of water and we put it in our kettle at home, atmospheric conditions in our kettle, well, we should remember from our college days that water boils at atmospheric conditions at 100 degrees. So if you remember that specific heat capacity we spoke about earlier, 4.19, it means that that kilogram of water that we put in the kettle, if we want to bring it up to a temperature of 100 degrees, we need to multiply it by 100. In other words, we're going to reach boiling point, but only when we've added 419 kilojoules of energy into it. And that's great. We've got boiling water now, but we don't want boiling water. We want steam. So we need to add a further amount of energy into that boiling water so it changes state from a liquid to produce steam. That water needs to fully evaporate. And the only way we can do that is by adding a further 2,257 kilojoules of energy to it. So once that water's disappeared, once it's evaporated, the resulting steam has got 2,676 kilojoules of energy within it. In other words, it's the energy that we put into the water to bring it to boiling point, plus the energy we then added to the water to make it evaporate. So this first column, we can refer to it as the enthalpy of water. We can also refer to it as the sensible heat. The next column, we refer to it as the enthalpy of evaporation. We can also refer to it as the latent heat. The column that's demonstrated here, that's the total heat energy. So when steam gives up its heat energy at the process, as we've mentioned, it condenses. It changes state from a gas to a liquid. It's the energy that's demonstrated in this column, the latent heat energy. The energy we added to the boiling water to make it change state. That's the energy that passes the heat transfer surface area into the process. Therefore, what's left behind in the liquid condensate must be the sensible heat that's demonstrated in this column. So that tells us that condensate is hot water. There is a value to it. But there's significantly less energy in that hot water than there is in the steam. That's why we need to get it away, because if we don't do so, we're slowing down the rate of heat exchange. So when the steam condenses, it changes state, gas to a liquid. The enthalpy of evaporation, or the latent heat, that leaves the steam and enters the process. The sensible heat is held back in the condensate. But when there's a release of heat energy, when the steam gives up its latent heat, there isn't a change in the temperature. In other words, the condensate is going to exist at exactly the same temperature and at exactly the same pressure as the steam. So if we move across to the temperature enthalpy curve now, this really demonstrates the journey that water takes as it changes state from a liquid to produce steam as a gas. We're using the example of 0 bar gauge, where we know water boils at 100 degrees. So it's only when we've added that 409 kilojoules per kilogram of sensible heat that the evaporation process is going to start. But it's only when we've added that 2,257 kilojoules of heat that we can say the evaporation process will have ended, and we've now got a mass of steam that is fully dry and fully saturated. Now that terminology, dry saturated steam, is critically important. It's the cornerstone of good steam engineering for a number of reasons. First of all, if we've got steam that is not dry and not saturated, it means we're going to have a lot of moisture entrained within it. And the wetter the steam, the more likely that steam is to condense out in the distribution pipework. And remember, we could be distributing that steam in steel pipework for hundreds, if not thousands of meters. So if that wet steam gives up its heat easily, we've got a lot of condensate. So that's a distribution loss. Could well be that we're generating 10,000 kilograms per hour of steam, but it could well be that if we've got a lot of condensate given up to the pipework, we're only actually getting 9,500 kilograms of steam to the process. It's an inefficiency. And if we've got a lot of condensate held back in the distribution pipework, well, we've got to remove it because it doesn't have enough heat energy within it to satisfy the process. So the more condensate we have, the more steam traps we need to install. That's going to be at some capital cost. And if we're holding condensate back, we're at risk of that erosion, corrosion, water hammer. That's when water exists within an infrastructure that's been designed to accommodate steam as a gas. And as that energy is released very, very quickly, as it's conveyed around the network at some speed, that's when we get a lot of crash banging, water hammer, vibration, damage to capital equipment. But as the steam is passing across that trapped mass of condensate, it's degrading, so it's getting wetter and wetter. And as the steam gets wetter and wetter, it's got less energy contained within it. So forget about the mechanical issues that we get caused by the erosion, the corrosion, the water hammer. Serious as it is, as far as the process is concerned, it means we get a reduced mass of steam distributed to the plant room. But the steam that does find its way to the plant room, it's going to have less energy in it as well. So the process time is likely to extend and extend and extend. Maybe we're going to fail to hit the required target temperature. Or it could well be that we get product spoilage as a result of a failure to heat the process up at the required time, all caused by the fact that we've got steam that is being produced and distributed in a very, very wet condition. The good news is we can make sense of both of these tables very, very quickly by downloading that very useful little app that we've spoken about. So the other things that the steam tables demonstrate to us is that pressure to volume relationship that we've spoken about. Now, a kilogram of water or a litre of water that goes into the boiler, when that changes state to produce steam, at atmospheric conditions, 0 bar gauge, it's going to have a volume of 1.673 cubic meters. But if we produce steam under pressure, say 10 bar gauge, then 1 kilogram of steam is going to have its volume greatly reduced, and it's going to then have a volume of 0.177 cubic meters. So this really demonstrates the benefit of increasing the working pressure, and that's going to enable us to distribute that steam hundreds, if not thousands of meters in a very small pipe diameter. But it also tells us it's critically important that we've sized the pipework correctly, because if we haven't, then it may well be that the steam wants to exist at a greater volume than the pipe has been designed to accommodate. And we also know that steam's got that direct pressure to temperature relationship that we've spoken about. The water that's boiling in our kitchen, in a kettle, 0 bar gauge, boiling point's 100 degrees. But if we increase the pressure of the boiler to 10 bar gauge, we can see that the boiling point of the water is going to be 184 degrees. Therefore, the temperature of the steam that's produced is going to be 184 degrees. But let's say we only want to use the steam at the heat exchanger at 2 bar gauge. It tells us that we can reduce the pressure to 2 bar gauge, and we're enjoying the temperature that the process requires, 132 degrees. Tells us that we can very, very easily control the release of energy from the steam into the process simply by using a 2-port valve. All we need to do is control the pressure to whatever point we get the appropriate temperature. The other thing we need to bear in mind is that steam gives up its heat energy by condensing, but when that steam condenses, there isn't a release of temperature. So the condensate or the steam that we're distributing in a pipework at 10 bar gauge pressure, the condensate is going to exist at the same pressure as the steam, and therefore the same temperature as the steam. And when we've reduced the pressure of the steam at the process, then the condensate will exist at the same pressure to temperature relationship. The condensate can exist as a liquid at that temperature because of the high pressure, and that explains why the condensate is so valuable to us in the boiler house, whilst not necessarily having any value to us at the process. So I want to look now at how steam is generated, and steam's generated in what we refer to as the energy centre, the boiler house, and it's quite a speciality. So some engineers they'll probably never get involved with the boiler or steam generation, but it's vitally important that we've got an understanding with regards to the basics of steam generation, because if we fail to do so, then it may well be that a poor condition of steam, it can have a significant impact on the process or on the overall health and safety issues around site. For example, if we've got steam that is distributed in a very wet condition, we're more at risk of that erosion, corrosion and water hammer of the various components around the distribution network. And we're more at risk of having a very, very inefficient release of heat energy across the heat exchanger and into the process. So I want to look at a number of key components that we use in the boiler house itself. In the middle of the screen, you can see a steam boiler. Well, Spirax Sarco don't manufacture steam boilers, but we do manufacture all of the components that you can see highlighted in blue. And they're basically the ancillaries and the controls that are responsible for ensuring that steam is generated efficiently from an energy perspective, that steam is being generated reliably, that the mass of steam is generated as and when the process requires it, that the steam is generated at an excellent condition. So it's as dry as it possibly can be to minimize the risk of that erosion, corrosion and water hammer. But most importantly of all, to ensure that that steam is being generated safely. So moving on from the boiler, one of the most important components in the boiler house is what we refer to as the atmospheric feed tank, or also known as the hot well. And this is where we want to recover all of that valuable hot condensate to. And we'll put a little bit of chemical water treatment into the condensate as well, just to make sure it's in the correct condition for going back into the boiler. We typically want to ensure that the hot well is held at a nice high temperature. So if you can imagine, if we've got hot water going into the boiler, it means we're getting less thermal shock and fatigue and failure of the boiler itself. It means if we put hot water into the boiler, it can produce steam very, very rapidly and responsively whenever there's a demand. Hot water going into the boiler, it means we need to add less fuel to it to generate steam again. But something that's often overlooked is hot water contains fewer oxygen and non-condensable gas particles than a lower temperature water. So it's inevitable that we may need to add a few conditioning chemicals into the hot well to polish off that last remaining oxygen content. So the rule of thumb is, well, the higher the hot well temperature, the fewer the chemicals we need to add. The lower the temperature, the more chemicals we need to add. So one of the first things we want to do when we enter the boiler house is look at the temperature gauge. See where the temperature gauge is hanging, because that is going to give us a very, very good indication with regards to the condition of steam that's being produced. And it's going to give us an understanding with regards to whether or not we're producing steam efficiently from an energy perspective. And of course, we know that if we're consuming more fuel to generate steam, the byproduct is that there are going to be more carbon emissions as well. So the sweet spot really is holding the temperature at around 85 degrees. We can't hold it much higher because if we do, we're at risk of a fall in pressure, creating a cavitation and a costly failure of the boiler feed pump. But if we notice that temperature gauge hanging there at a point that is significantly less than 85 degrees, for example, if it's there at 50 or 60 degrees, it tells us there's an excellent opportunity there to recover more condensate and also to understand the impact that can have on improving the steam generation. So we also know that perhaps the next most important component in the boiler house, well, it's the level controls. And the level controls can either be mounted internally or in chambers outside the boiler. And they can be of a number of different types. They can either be a very basic magnetic float type. They can be a conductivity probe type, or they can be a capacitance probe type. Now, each different type of probe will have a different daily testing and supervisory regime requirement. The main purpose of the boiler level control is, first of all, to ensure that there's the appropriate level of water within the boiler. Too low, the boiler can run dry and fail. Too high, and we're drawing an excess of water, not wet steam, water into the distribution pipework, and it could be waterlogged. So the level control probe, first of all, it sends a signal to a feed pump to call for the appropriate mass of water. And if that water level reaches a dangerously low level, it will send a signal to fire an alarm and switch the burner off. If it reaches a high level, it will switch the feed pump off. And there are different types of feed pump as well. There can be what's referred to as an on-off pump or a modulating pump. An on-off pump, well, that typically turns the pump on when the water level reaches a low point and off when it reaches a high point. And the difference between the low and high points can be a significant mass of water. So if that water's cold, if it's significantly below 85 degrees, that means that it can create a quenching effect and a slowdown in the mass of steam that's being produced. It can also mean that as the boiler's racing to put enough energy into the water to raise steam, that steam that is being produced in those first few moments is going to be wet. So it's far better if we can move away from a on-off pump to a modulating pump. And that works by constantly drip feeding in a very, very small mass of high temperature water into the boiler. So the boiler can ensure that the steam is being produced in equilibrium with the requirements, and it means we don't get that quenching effect. It means that we've got steam that is more readily available. We get a better condition of steam being produced for the process. And it also means we're working more efficiently from an energy perspective. And then we know that we've got to maintain the water chemistry of the boiler. If we're putting all those chemicals into the feed water, that together with the chemicals and minerals that are present in the raw water, it means that over time, as the water's evaporating to produce steam, we're going to find that a lot of the particles, a lot of the minerals will solidify and fall to the bottom of the boiler as a sediment. And over time, that can back up past the heat pipes and create a critical failure. We need to get rid of that sediment, and we do so by opening a little valve that we refer to as a blowdown valve, and that sits underneath the boiler. So the boiler will be operating at a high pressure, 10 bar gauge, for example. Any fall in pressure across the blowdown valve, that's going to result in a blast action of a relatively small mass of very, very high temperature, high pressure water being blasted across the valve and dragging all of that particulate with it. And it's nasty stuff. It's got a lot of heavy solids and particulate present within it. So we can't really use it anywhere else in the process. It does need to go to waste. But we also need to bear in mind that if we don't blow down enough, then we're not getting rid of that sediment. We run the risk that it can cause a problem with the steam condition and cause a problem with the mechanical working of the boiler. But if we blow down too much water to waste, then we're losing a significant amount of hot water. We've got to replace that hot water. The level control probes will call for the appropriate mass of colder water to be replaced. We're getting a delay in the amount of steam that's going to be produced. We get an inefficiency because we've got to bring that water up to the point where it can produce steam again. But it also means the steam that is produced in those first few moments is going to be relatively wet. So we can perform that blowdown manually, or we can move towards an automated system that we'll discuss in a few slides' time. The thing is, that hot water, that blowdown, it does need to go to waste. And it goes via what we refer to as a blowdown vessel. And the purpose of the blowdown vessel is, first of all, if we get a fall in blowdown temperature or pressure from 10 bar gauge, 184 degrees, to atmospheric, 100 degrees, in a very short period of time, we're going to get a lot of flash steam being produced, a lot of energy being released. So first of all, the blowdown vessel releases that energy very, very safely. And secondly, it allows that liquid blowdown to cool down before such a time that it can be displaced to the town's effluent system. It typically needs to cool down to a temperature of 43 degrees or less, so it can remain compliant with the Water Treatment Act of 1990. And then we also perform blowdown at another area, and we refer to this as the TDS blowdown, total dissolved solids. So whereas some of the chemicals and minerals will solidify and fall to the bottom of the boiler as a heavier sediment, some of the chemicals and minerals will be held in suspension. We refer to that as the total dissolved solids. So as water's being evaporated to produce steam, the chemicals within the boiler can become progressively more and more concentrated. And they'll reach a point whereby it causes a lot of foaming to occur on the surface of the water level within the boiler. And that's an indication that the heating elements are starting to scale up, and that's going to result in an inefficiency, a loss of heat transfer, an increase in fuel demand. But as we get a fluctuation in pressure, then that foaming layer can expand and it can be drawn out of the boiler into the distribution pipework. And that foam's going to be very wet and sticky. So first of all, it's going to contribute to that wet steam that we spoke about. It's going to contribute to that erosion, corrosion, water hammer effect. But that foam is also going to dry out as scale. And that scale can be conveyed in with the steam. It can block steam traps, it can block strainers, it can create erosion of sensitive areas. It can bind itself to heat transfer surface areas, resulting in an insulating effect or a slowdown, certainly a burden of maintenance. So we want to ensure that the water chemistry is held at the correct point. The TDS needs to be at an appropriate level, and we measure it in parts per million. So typically the TDS could be managed by taking a sample from the side of the boiler on a daily basis, putting conductivity probes across that cooled sample. High conductivity, it's an indication of a high concentration. We open a valve at the side of the boiler. We bleed out a couple of gallons of hot water to waste. And then when the water level's fallen, it's replaced with a mass of colder water from the hot well. But again, the more TDS we're blowing down to waste, the greater the inefficiency from an energy perspective. And it also means that as we race to bring that water up to the point where we can produce steam again, well, we're more likely to get wet steam being produced in those opening moments. So it's critically important to hold the amount of blowdown that's being performed, both from the bottom of the boiler and from the TDS at the appropriate point. But the one thing that it sets the TDS blowdown apart from the bottom blowdown is there's no nasty heavy particulate or abrasive particles present within it. So that means the TDS is in an excellent condition for being passed across a very basic heat recovery system. So we can pass it across a flash vessel. We can add the resulting flash steam into the hot well to help keep it at a nice high temperature, and pass that residual blowdown across a heat exchanger. So we're adding some heat energy to the raw makeup tank. And by taking the heat energy out of the blowdown, it also means we've got the benefit of ensuring it can cool down to a point where it can be dumped to waste very, very quickly. So a TDS heat recovery system, it can offer a very, very attractive payback, typically in the region of 12 to 18 months for any site, depending upon the mass of hot water that they are typically dumping to waste. And another important component of the boiler house that's often overlooked, it's the steam meter. We need to meter the mass of steam that is leaving the energy centre and entering the distribution network, because it's only by doing so that we can understand the true efficiency of the steam boiler and the true cost of steam that is being produced. And there's another benefit, because if we've got another meter, hundreds, thousands of meters away at the process, well, we can determine if the mass of steam is arriving at the rate that we expect. In other words, understanding if there's any leaking steam traps or leaking valves somewhere around the distribution pipework. So steam using sites have got a lot of standards and legislation that they need to abide by. And perhaps the most important standard here that's jumping out is what we refer to as INDG 436. It's a document that's written by the Health and Safety Executive here in the UK and closely referenced by a number of other countries. And essentially it's a risk assessment. So it allows the senior managers or directors of a steam using site, it allows them to understand what their obligations are to ensure that they've got a steam boiler that is operating safely. But then again, there's a number of other documents. We refer to them as the BG documents, BG standing for boiler guidance. And the important thing to bear in mind here is it is guidance. So a steam using site may choose not to follow this guidance, But as with all things, if there were to be a serious health and safety event on a steam using site, if it was proven that guidance was available but hadn't been adhered to, then there'd be serious questions to ask there. And certain boiler guidance documents, they'll refer to different aspects of managing the controls and supervising the boiler house itself. For example, BGO1, that would refer to the installation, operation, daily testing and supervisory requirements of the level control probes. Remember, there are different types of level control probes. They can be magnetic, they can be conductivity or capacitance type, and they can be mounted internally or externally to the boiler. And then we've got BGO3, and that refers to the safe operation, the daily testing regime and supervisory regime of the blowdown controls, both for the TDS and for the bottom blowdown. The thing to bear in mind is that these documents, these BG documents, they're all written by the Health and Safety Executive here in the UK. So the Health and Safety Executive, they don't care whether we're producing steam efficiently from an energy perspective. They don't care. That's not their problem. They don't care if we've got a huge amount of carbon emissions as a result of consuming more fuel and producing steam inefficiently. Not their problem. They don't care if we've got a huge burden of maintenance as a result of that erosion, corrosion and water hammer caused by wet steam. They don't care if that wet steam is resulting in a lack of energy being imparted to the process. It's simply not their problem. What they care about is ensuring that the steam is being generated in the boiler safely. So it's for that reason that there are so many different boiler control types. It's for that reason that there are so many different level control types, that there's an on-off pump and a modulating pump alternatives. It's for that reason that we could choose to blow the bottom blowdown manually, or we could choose to upgrade and retrofit a timed actuator onto it so we can do it automatically. It's for that reason that we could remove the TDS from the boiler manually, or we could choose to do it automatically by using a conductivity probe ahead of a modulating valve. The boiler industry is a very, very competitive industry. So unless the client or the consultant specifically advise the boiler manufacturer what their requirements are, then it's highly likely that the boiler manufacturer will offer the most basic controls in order to remain competitive. The good news is that we can retrofit all of those controls onto an existing steam boiler with a proven payback and with very, very little disruption to the wider steam distribution network. So it's at this point, once the steam has left the boiler house, this is when it enters what we refer to as the distribution network. And if we're not passing an excellent condition of steam into the distribution network, we're never going to get a good condition of steam at the process. The process time is likely to be quite lengthy, and it means we're likely to experience those maintenance issues as the steam is being distributed that distance, the erosion, the corrosion, the water hammer, for example. So we want to ensure that we're distributing or generating the best possible condition of steam that we can. So I'd just like to summarize at this point here. What we've learned this evening is that steam is a very, very efficient method of distributing heat energy from the point of generation to the point of use. We know that steam's a gas, therefore we don't pump it. It's easy to distribute. It moves in accordance with the pressure drop around a network. It's easy to control. We can break the heat energy down simply by using a two-port pressure reducing valve. Very, very easy. Control the pressure and we're manipulating the temperature. And we also know that it's crucial that we understand that the steam needs to be generated in the energy center at the best possible condition. If we're not doing that, we're never going to have a system that is free of maintenance or is working efficiently or responsively. But the good news is that if we recognize the signs that steam isn't being generated efficiently, then we can improve upon that very, very easily by retrofitting enhanced controls, better boiler level controls, more sophisticated feed pumps, and automated blowdown controls very easily with a proven payback. But we also want to periodically monitor the condition, both of the steam, of the controls, and of the steam traps to make sure we haven't got any unexpected losses as the steam moves from the point of generation to the point of use. So this evening, hopefully we've understood the basics of steam system fundamentals. And if there is an appetite in coming weeks or months to journey further around the steam and condensate loop, we can move on to the other topics, such as understanding how we need to employ the good working practice to distribute the steam from the energy centre to the process, and so on and so forth. So on that note, I'd like to thank you very much for your time in attending today's CPD presentation. If any of you would like a PDF of the slide pack or a PDF of an attendance certificate, please don't hesitate to reach out to me. I'll be more than happy to make that available for you. I will put my contact details up on the slide pack here, so you can contact me if that should be a requirement. Please don't forget to consider downloading that very, very useful Spirax Sarco Mexico app. Many of you will find it very, very useful. And so at this point, I'd just like to invite Murat to open up the microphone and see if there have been any questions that have arrived as a result of this evening's topic.
Hi, Dan. Thank you. Thank you so much for this presentation. I think you delivered it so well. Amazing stuff. I have got a few questions for you, and I'm hoping more people will also submit their questions through the chat box in the meantime. Can I start with sort of asking, what is the typical steam pressure in the distribution pipeline? I mean, you mentioned when we increase the temperature, the pressure is also changing. So what is the typical pressure that they distribute these steams?
Well, it really depends on two factors. First of all, how far we're distributing the pressure, how far we're distributing the steam, and also the temperature of the steam that is required by the process. For example, if we've got a steam using heat exchanger that only requires steam at 132 degrees, the steam at that point is only required at 2 bar gauge.
Okay.
So the amount at which we can actually compress the steam, it starts to plateau off round about 10-12 bar gauge. So unless we specifically need the steam to exist at a very, very high temperature, there isn't too much of a benefit in distributing steam much beyond 12 bar gauge. So generally you'll find for the vast majority of industrial applications, the distribution pressure will vary between, say, 7 bar and 12 bar at the upper end.
Excellent. That makes sense actually. I've got a question here, another one. Does heat transfer coefficient of steam depend on the steam's velocity, like water heat transfer coefficient, or effect of velocity on heat transfer coefficient is pretty much negligible?
Again, it really depends upon what the steam is being distributed for. For good working practice and general wear and tear, we don't want to be condensing the steam at a very, very high velocity, because if the steam is wet, then those moisture particles that are conveyed within the steam, they're going to have a very, very abrasive effect, almost like a sandblasting effect. If you think about steam being distributed at 40 meters per second, for example, that's somewhere close to 70 miles per hour. So even a few drops of moisture passing across a sensitive area like a heat exchanger or a control valve at that velocity, it's going to create a lot of damage and a lot of noise. And of course, when steam gives up its heat energy, it condenses. So if we've got a high velocity steam that's passing into an area that's full of condensate, we're going to get a lot of noise, a lot of damage, and even further erosion. So as a rule of thumb, we typically want to see a pressure drop whenever we're condensing the steam. We want to condense the steam at a very, very low pressure, because we've got a greater efficiency. We've got a more rapid speed of heat transfer. The steam tables actually demonstrate that there's more energy present in steam at a lower pressure than there is at a higher pressure. More useful energy, more latent heat energy. So for that reason, heat transfer and high velocity aren't concepts that are generally considered to be interchangeable.
So the larger the pipe, the better, actually, you mean? But we don't want to use large pipes for the cost effects, I suppose. Is that right then?
Exactly so. Exactly so. If we're distributing steam in a large pipework at a low pressure, then we've got a large heat transfer surface area. We're going to get more condensate. We're going to get we're going to get a greater inefficiency, and that greater condensate load is going to result in more of that erosion, corrosion, and water hammer that we spoke about.
Okay. Yes.
Distribute steam at high pressure, and use the steam at the process at a lower pressure.
Okay. Okay. Fair enough. That sort of brings me to another question about failures. Really, is it possible to then burst the steam pipelines if they are cooled down very fast? Is that something happens in the field?
Yes, I mean we don't want the temperature of the pipework to fluctuate too much or too quickly. For example, if we're bringing a steam distribution network up to pressure and up to temperature, we want to do it slowly over a number of hours. Because if you think about it, if we're distributing steam hundreds, thousands of meters, if we're putting a very, very high pressure and high temperature, 10 bar gauge, 184 degrees onto that steel pipework, it's going to expand.
Yeah.
And if we get expansion, then we can get damage to capital equipment. We can get the flanges and the fittings twisting and damaging. We can get leaks.
Okay. Yeah.
But it also means if we're bringing the temperature and pressure up quickly, we're going to get a lot of steam giving up its heat energy to the infrastructure. We're going to get a bigger heat loss before the steam actually reaches the process. That means we're going to get an increased condensate load. And that means we're at risk that the steam traps could now be under capacity. Then we're at risk of that enhanced erosion, corrosion, and water hammer because we're not able to drain the condensate away at the appropriate rate. So we want to ensure that a steam system is warmed up slowly. And with regards to your question about it cooling down too quickly, well, that's one of the reasons why we encourage you to have lagging or insulation at the appropriate point on a steam pipe. Not only does it protect it for health and safety purposes, banging our heads against a hot pipe, it also helps us to keep the steam dry, reduce those losses, but it also protects the steam pipework and the infrastructure from any excessive wear and tear that can be introduced by warming up or cooling down too quickly.
Okay, yeah. The thermal fatigue associated with the pipework, I understand.
Exactly.
Another question here then is how much non-condensable gases influence heat transfer coefficient of steam in a heat exchanger? Should we consider any margin for heat transfer surface?
Well, it's a huge problem. It is the biggest problem in heat exchangers is a failure to get rid of that insulating film of air. The good news is that we can eliminate it very, very easily using a thermostatic air vent. And we can't use a mechanical air vent because a mechanical air vent works on the density principle that steam as a gas and condensate as a liquid have got different densities. But the insulating properties of the air mean that it's going to exist at a different temperature to the steam. So a thermostatic air vent will allow the steam pressure to push the air away, at which point we're moving towards a position where we've got dry saturated steam.
Okay.
So you're right to identify it as a problem. If you think about a sterilizer in a hospital, this is just one example. Well, we've already mentioned that we control the temperature of the steam by manipulating the pressure. So if we need to hold a porous load in a sterilizer in a hospital at 132 degrees, we can achieve that by delivering steam or by controlling the pressure of the steam to a pressure of 2.1 bar gauge. Now that's all well and good, but that assumes that we've got a mass of steam that is 100% dry and 100% free of air. If we don't have clean, dry steam free of air, then we can no longer rely on that pressure to temperature relationship. And that's why air venting is critically important.
Okay. I mean, you also mentioned the corrosion and everything. So what would be the most common pipe material used in the boilers and the pipe work?
Well, the most common pipe work that we would use would typically be shed 40 API pipe or shed 80 API pipe, depending upon the pressures. Carbon steel for the vast majority of plant steam systems. It's interesting you mentioned corrosion, because the biggest cause of corrosion, again, is air. So that's another reason why we want to vent the air away. If we see pinholing or an excess of rust in the distribution pipework, the problem is likely down to having too much air in the system. Right. So we chemically treat the water in the hot well to protect the boiler from corrosion.
So dry steam doesn't cause any corrosion at all?
Dry steam, it can cause corrosion, but the problem is it's the air that comes, if we've got wet steam, it's the air and the other non-condensable gases that become reabsorbed back into the condensate. The condensate will then slowly turn into carbonic acid. So yes, it is the condensate caused by wet steam that causes corrosion, but if we're venting the air away appropriately and if we're removing the condensate at the appropriate rate, then for the vast majority of well-designed boiler houses and boiler and steam distribution networks, that isn't going to be too much of an issue.
Right. You also mentioned we have thermal expansion. I assume the pipe work will then fatigue as well because of these changing temperatures and everything. I mean, is there anything the industry uses? I'm not familiar with the steam industry apparently.
Yes,
so.
we've got calculators and configurators on our website that can give guidance with regards to the amount of expansion that you can expect if we know a number of key variables. For example, if we know the mass flow rate of steam, if we know the pressures, the temperatures, if we know the diameter of the pipework, the material of construction, the linear run of pipework, the ambient conditions outside, if we know the grade of insulation, then we can give guidance with regards to how much expansion you can expect.
Right.
And then typically a structural engineer or a stress analyst, they will then make a decision with regards to how to protect against that expansion and where to place the anchor points.
I understand, appreciate it. It is actually 7 o'clock right now, so I will sort of bring this to a close, Daniel, if that's okay. I would like to thank you so much for this. I will also ask everybody, if that's okay, to unmute yourselves for a second and maybe give Daniel an applause, or maybe if you want to use the applause function, how do you call this? Yes, that's exactly it. People understand what I mean.
That's a new one on me. Never seen that one before.
Thank you all very much. With that, again, I'd like to thank you all and remind you that we also have further events, other events on our IMechE website. We also have some membership support if you are ever interested. We are hoping also Daniel will be able to present some further lectures for us about STEAM as well. Please follow us through our social media and IMechE events. And thank you all very much for joining our event.
Thank you.
Thank you, Daniel.